So we're considering just these two, and we're considering a mother and father with the following genotypes. And we're going to look at all the possible combinations. We'll start with mom for her eggs. So we've got 4 possible combinations for her eggs. And despite the fact that I keep saying the big letter goes in front, that's if we're talking about 2 alleles for the same trait. In this case, we leave it like this because these are 2 different traits that we're dealing with. Well, what does this look like when we go to do a Punnett Square? Let's go to the next page. Instead now of just doing big T, little t across the top for mom's contribution, we have to put all of these possibilities across the top. So the top is now going to look like, actually, see if I can do this cleverly. Paste. Cut. Okay, so across the top we have this. Okay, well, what about Dad's contribution? Okay, so Dad's going to be a little bit easier. For every sperm that is made in Beaver Dad's testes, what are the options for it to get in terms of alleles for tail length? Little t. Dad's got nothing else to give. Every single sperm that this beaver manufactures is going to have a little t. That's all he's got. Well, what are the options for nose length alleles, or nose color? Big N. So guess how many options Dad has for alleles here? Big N. All of his sperm will be identical. They will all be little t, big N. That's all he's got. So how do we put this into a Punnett Square? Well, little t, big N. That's it. I can actually move this up. We don't need all of the space that we have. So this is going to be a 4 by 1. Okay. So now we do a Punnett Square just like we've done all the other Punnett Squares, but we're going to put the alleles together. So here we would draw down the T's. We get big T, little t, big N, big N. We get big T, big N, little n. Little t, big N, big N. Little t, big N, little n. Okay? It's pretty easy. This is called a dihybrid square. We still figure out our genotype and phenotype ratios. So how many possible combinations of genotype do we have? And we have to look at both of them. So we have big T, little t with big N, big N. That's that one. We have big T with big N, little n. They're all different. We have little t with big N, and little t with big N, little n. And how many of each of them do we have? 1, 1, 1, and 1. So what's our ratio? 1 to 1 to 1 to 1. That's pretty easy. What are our phenotypes? So this one gets a little bit trickier. No, I don't want to do that. Don't want to do that. Okay, let me see if I can cut that. Okay, so we have to look at the genotype or phenotype for each trait. So big T, little, so we could have a, actually I'm going to copy some of this over to the other page, hold on. Okay, we have 4 possible phenotypes. We have long-tail black nose, long-tail pink nose, short-tail black nose, short-tail pink nose. If we look at our 4 genotypes for our offspring, looking at this first one, long-tail or short-tail? Long, what color's the nose? Black. And looking at the next one, also long-tail black nose. So we have 2 long-tail black nose. How many long-tail pink nose do we have? 0. Nobody has a pink nose. None of these 4 have pink noses. This one, long or short tail? Short. What color's the nose? Black. So that's 1, and what about this one? Short tail, black nose. So we have 2. So this is a 2. The phenotype ratio is 2 to 0 to 2 to 0. Let's do one that's a little bit tougher. What is the cross that gets you the most variation in offspring when you have 2 what kind of parents? 2 heterozygous parents means lots of variety. So let's look at a litter of beaver babies from 2 heterozygous parents. Let's say we have mom, who is big T, big N, little n. Dad, who is the same. Okay. So when we start off by figuring out what possible combinations exist in the gametes, for every egg mom creates, it can have either a big T or a little t, right? It can have, every big T egg can have a little n or big N or a little n. Every little t egg can have a big N or a little n. So mom has T big N, big T little t big N, little t little n. Well, what does dad have for possibilities? Same thing. So dads are going to be identical. We can actually just copy this whole thing. Okay. So our dihybrid Punnett square for this combination is going to be a 4 by 4. Copy. Paste. Expand that a little bit. And then down the side, T, big N, big T, little t, big N, little t, little n. Okay. Start crossing. I'll start crossing up here. You start crossing on your paper. Holy moly. Do you have the same thing I do? Zach, wake up. Start crossing. checking your work. I see a few of you checking. So now we start to do genotype ratios. So big T, big N, big N, big T, big N, little n, big T, little n, little n, big T, little t, big N, big N, big T, little t, big T, little n, big T, little n, little n. Holy moly. Little t, big N, little t, big N, little n, little t, little n, little n. Hoi. Now this is where I always, I cross them off as I go, or I screw it up. And a few of you I saw were using like tally marks. That's a great way to do it. So I'm going to use colors because I have a color here. So I see one of those, and that one's crossed off as counted. I think that's the only one of those I have. Big T, switch colors. 1, 2. Big T, little n. One of those. Okay. So hey, what does that look like? Looks like our 1, 2, 1. Well, let's keep counting. So big T, big N, big N. Big T, little t. I see one there. I see one there. Any others? Okay. Big T, little n, little n. Big T, big N, little n. 1, 2, 3, 4. Okay. Big T, little n, little n. 1, 2. Anybody see anything I'm missing? Did I miss any? You count on your own paper, hopefully. Little t, big N. 1, I only see 1. Big T, little n. Big N, little n. 1, 2. And we should have one of the last kind, which is the little. Do you have a pass? Okay. So we only have one of that. Holy moly! Let's translate those into some numbers. So 1, 2, 1, 2, 4, 2, 1, 2, 1. Yikes! You think you can just remember those numbers? Probably not. Probably not. But where's the biggest percentage? If we were to break that down into percentages, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, we have 16 offspring. 4 out of 16 of those offspring are heterozygous for both traits. So what percentage is 4 out of 16? 25%. So even in this big whole thing, 25% of your offspring are heterozygous for both traits. Do you see how these get kind of overwhelming pretty fast? So what I want you to do is on your paper, pick 2 traits and start a dihybrid. Well, wait, first we have to do the genotypes, don't we? I'm sorry. We have to do the phenotype ratios. So let's shrink this. Let's look at the phenotypes. Okay. So what phenotypes do we have? We have long tail, black nose, long tail, pink nose, short tail, black nose, short tail, pink nose. Not so many kinds, just 4. So all of these are going to fit into those 4. Okay. So how many of each of them do we have? Well, we have to go back and look at these guys. Okay, we have to go back and look at these. So for each of these, what you're going to do is say, well, for this one, is that a long tail or a short tail, black nose or pink nose? Yeah, long tail, black nose. Actually, that one's long tail, black nose. There's one. Who else has a long tail and a black nose? That one. That makes 3. There's a long tail, black nose. 4, 5. There are 4 long tail, black noses. 1, 2, 3, 4. Okay, that's all of them. So we have 9. I'll replace this with a number. We have 9 long tail, black nose. How many long tail, pink noses? Let's switch colors. Long tail, pink nose. Long tail, pink nose. 1, 2, 3. Short tail, black nose. We'll switch colors yet again. Short tail, black nose. 1, 2, 3. And how many have a short tail and a pink nose? Just 1. We're left with just 1. That's the little oddball in the litter of 16. That's the one who doesn't look like any other siblings. It's the least likely combination to have, genotypically. Because that one is showing recessive for both traits. Okay, when we start tomorrow, what you are going to do, you're going to have all your papers again. You're going to pick 2 traits and do and then do all the genotype and phenotype ratios for that. Okay? That will lead us to tomorrow. Have a good day.